You've sourced a pile of coarse aggregate for your project. It looks clean and hard, but looks can be deceiving. What if it's full of soft, porous particles that will crush under load? Or what if its particle size distribution is wrong, making your concrete harsh and unworkable? Using untested aggregate is like building a house on an unknown foundation. It's a massive risk. The coarse aggregate makes up 60 to 75% of the volume of your concrete. Its properties directly dictate the mix's strength, durability, and economy. In this video, we're going to demystify the essential quality control test for coarse aggregate. I'll walk you through the key tests, from a simple sieve analysis you can do on-site to the sophisticated lab tests that predict long-term performance. This knowledge is fundamental for anyone who wants to produce high-quality, durable concrete, not just hope for it. Let's start with the most fundamental test of all, the sieve analysis, or gradation test. This test determines the particle size distribution of your aggregate sample. Why does this matter? A well-graded aggregate, meaning a good mix of various sizes, has less void space. Less void space means you need less cement paste to fill those gaps, making your mix more economical and often stronger. It also drastically improves the workability of fresh concrete. The procedure is straightforward but requires precision. We take a representative sample of the aggregate, dry it, and then pass it through a nested set of sieves arranged from largest opening at the top to smallest at the bottom. The sieves are shaken mechanically for a standard period, typically 15 minutes. After shaking, we weigh the material retained on each sieve. This data is used to calculate the cumulative percentage retained and passing for each sieve size. We then plot this on a gradation chart and compare it to the specification limits, like those in ASTM C33 or the relevant IS code. A pro tip from concrete technologists: a gap-graded aggregate, which is missing certain intermediate sizes, will often result in a harsh mix that is difficult to finish and may be prone to segregation. The sieve analysis is your first check to see if the aggregate is even suitable for use. Now let's talk about strength. The aggregate particles themselves need to be strong enough to resist crushing under load. We have two key tests for this. The first is the aggregate crushing value test. This test measures the resistance of aggregate to crushing under a gradually applied compressive load. We take a sample of aggregate passing a 12.5 mm sieve and retained on a 10 mm sieve. We fill a standard cylindrical mold in 3 layers, tamping each layer 25 times. Then we place the assembly in a compression testing machine and apply a load of 40 tons over 10 minutes. The load is released, and the sample is sieved on a 2.36 mm sieve. The aggregate crushing value is the percentage of material that passes the sieve, indicating the crushed material. A lower percentage means a stronger aggregate. The second test is the aggregate impact value test. This is similar but measures the resistance to sudden shock or impact, which is a different type of loading. In this test, we fill a standard cup with aggregate, and a hammer weighing about 14 kilograms is dropped 15 times from a height of 380 millimeters onto the sample. The material is then sieved on a 2.36 mm sieve, and the percentage passing is the aggregate impact value. For both tests, lower values are better. For high-quality concrete, the crushing value should ideally be below 30%. A common mistake is to assume that hard-looking stone is strong. These tests provide the quantitative data to prove it. Concrete aggregate doesn't just sit there. It gets abraded, walked on, and subjected to weathering. This is where durability tests come in. The most important is the Los Angeles abrasion test. This is the globally accepted test for determining the hardness and abrasion resistance of aggregate. In this test, we place the graded sample of aggregate along with a specified number of steel charge balls into a large rotating drum. The drum is rotated for 500 or 1,000 revolutions at a speed of 30 to 33 revolutions per minute. As it rotates, the aggregate and steel balls tumble against each other, causing abrasion and impact. After the test, the material is sieved on a 1.7 mm sieve. The Los Angeles abrasion value is the percentage of wear, or the percentage of material that passes the 1.7 mm sieve. A lower value indicates a tougher, more durable aggregate that will resist weathering and wear in pavements and floors. For high-quality concrete, a value below 30% is typically specified. This test is so critical for pavements that it's often non-negotiable. A pro tip for site engineers: if you're using local aggregate with a marginally high LA value, you might need to adjust the mix design or reserve it for less critical applications. The physical characteristics of the individual particles are also vital. This is where the shape tests come in, the flakiness index and the elongation index. Flaky particles are those whose thickness is less than 0.6 times their mean sieve size. Elongated particles are those whose length is greater than 1.8 times their mean sieve size. Why do we care? Excessive flaky and elongated particles are problematic. They require more water in the mix to achieve workability, which can weaken the concrete. They also break more easily, create poor particle packing leading to more voids, and can make the concrete difficult to compact properly, resulting in honeycombing. To determine the flakiness index, we pass the aggregate through a set of elongated slot gauges. The particles that pass through the slots are considered flaky. The elongation index is determined using a length gauge. A high percentage of these irregular shapes is a red flag, and you might need to request better shaped aggregate from your supplier or adjust your mix proportions to account for the reduced workability. Finally, we have the fundamental tests of specific gravity and water absorption. These two properties are determined together and are incredibly important for mix design. The specific gravity is the ratio of the weight of the aggregate to the weight of an equal volume of water. It indicates the density and solidity of the aggregate particles. A higher specific gravity often indicates a stronger, more durable material. Water absorption, as the name implies, measures the amount of water an aggregate can absorb into its pores. This is crucial because if the aggregate is highly absorptive, it will steal water from the mix, reducing workability and affecting the water-cement ratio. We determine these by weighing the aggregate in three conditions: oven dry, saturated surface dry, SSD, and submerged in water. Using these weights, we can calculate bulk specific gravity, bulk SSD specific gravity, apparent specific gravity, and the absorption percentage. For a quality mix, you want a high specific gravity and a low water absorption value. A high absorption value means you must pre-soak the aggregate or carefully account for the absorbed water in your batching calculations to avoid a disastrously stiff mix on site. These values are not just numbers. They are direct inputs into your concrete mix design software and calculations. In conclusion, testing coarse aggregate is not a bureaucratic hurdle. It is a fundamental engineering necessity. Each test gives you a piece of the puzzle. The sieve analysis tells you about workability and economy. The crushing and impact test tell you about strength. The LA abrasion test tells you about durability. The shape test tell you about compactability. And the specific gravity and absorption test feed directly into your mix design. By rigorously testing your aggregate, you are no longer just buying gravel. You are specifying a high-performance engineering material with known properties. This proactive approach is what ensures your concrete structures will be strong, durable, and cost-effective for decades to come. Now I want to hear from you. Which aggregate test have you found to be the most revealing on your projects? Was it the sieve analysis that explained a workability issue, or the water absorption that caught a mix design error? Let me know in the comments below. If this guide to aggregate testing has been valuable, please give this video a like and subscribe for more content that helps you build with confidence.